air movement. When we often focus on installations, infiltration is actually frequently the silent killer of building efficiency. By definition, infiltration is the uncontrolled leakage of outdoor air into our conditioned space. The key word here is uncontrolled. Unlike mechanical ventilation, which we designed and cycle to ensure occupant health, infiltration happens by through cracks and gaps in building envelope. We also have to look at the HVAC balance. If a building's exhaust fan are pulling out more air than the supply fan, right? Exhaust more than supplied, then um, then it will bring the building will falls into negative pressure because you're drawing more air out of the buildings, so creating that negative pressure. This effectively turns the building into a vacuum, sucking unconditioned outside air through every tiny openings in the envelope. Right? Air will find any tiny spaces in building envelope and then go through them. Also, we pay respect to the law of physics, right? Wind velocity. Wind velocity and stack effect. Wind creates a high pressure zone on the side of the building where the wind physically pushing air through the wall. Stack effect act like a chimney because warm air is less dense and rises. It escapes out of the top of the buildings and create the suctions at the bottom that pull cold air in during the winter time, right? So what we do during the audit is to find this pressure point. If you can stop the air from escaping the top, you often stop it from sucking in at the bottom. So here shows the how wind velocity, if the wind is blowing on one side, right, the blue arrow here, and that creates the high pressure side of the building, pushing air into the building, and the relative low pressure on the other side, the air from inside the building will leak to the other side. So you have unconditioned outdoor air going into the buildings and conditioned air being pushed out of the building simultaneously, right? These arrows indicate the direction of the pressure, okay? Stack effect, right? Stack effect. Here you can see the high-rise building here. The somewhere in the middle, right? You might be able to read neutral pressure plant. That means below that plant, you can see during the winter time, because we use heating inside the building, and heat is tend to rise upward, and that create a suction at the bottom, right? Create suction at the bottom and air being pushed out on the top. So the largest pressure would be at the floor, the first floor. During the summertime, everything's reversed. You still have that neutral plant, right? You should have that neutral plant, but now we are using what? Air conditioning. When we are using air conditioning, the air is cooler, denser, so tend to go down, right? Tend to go down, and that push air out at the bottom floors, and therefore air will be drawn in on top floor. Okay, so that's called stack effect. So for infiltrations, just a sensible load, you can use this equation. Q dot equal to V dot rho Cp delta T. Q dot is the rate of heat transfer in terms of watt or BTU per hour, depending on metric or inch-pound unit that you use. V dot is the volumetric flow rate. That's how the infiltration rate. And rho Cp is the density, specific heat, property of the air. Okay, and of course, the temperature difference, indoor-outdoor air temperature difference, right? So using this, you can estimate the rate of heat loss or heat gain during the summertime due to infiltration, right? Due to infiltration. Here you have you see this figure here. You got different lines, right? Each line indicates the size of the door, right? The size of the door. Here on the horizontal axis, you see the time door is opened, how many hours per day. The vertical axis here is the total annual heat loss, and the unit is millions BTU per year. So infiltration, the heat loss due to infiltration depends on how often the door is open and closed on the, when you walk into an office building. Sometimes when you open a door, you will see a draft rushing into the building. So how often the door is opened, and also how the size of the door, okay, and you can estimate the heat loss due to infiltration. Now, depending on the location and depending on, there are assumptions when this figure was created, right? So here are some of the assumptions. The figure is based on 6 months heating season, mid-October to mid-April. Here we might have slightly longer heating season, I would say, right? But that can be adjusted. Also, it's using an average wind speed of 4 miles per hour. Okay, and assume that the heated building is maintained at 65 degrees Fahrenheit, around, I think, 17, 18 degrees, right? It can be adjusted for different conditions. For example, if we read the Q from the figure, that's unadjusted, and the figures for 5 days a week, right? The building is open 5 days a week. So D here is the number of days. If the building opens 7 days, then we will use 7 divided by 5 there to account for the different number of days. Because the chart is using 65, heat to 65, so we have 65 here. If the heating is up to, say, 70 degrees Fahrenheit, which is pretty typical for winter residential buildings, right? But anyway, 65. T is the outdoor air temperature, the average outdoor air temperature. So whatever that is, if the location, say Toronto, what would be the average ambient air temperature for the whole heating season? I'm not sure. -5, 0 degree, okay? And then finally divide by 13. Okay, divide by 13. 13th was the so that 13 there is the let me check. 13 is the temperature difference. So it was 52 Fahrenheit at the location. I think this chart was created by Georgia Tech. Can't remember the name. Okay, so they have the temperature difference 13th. and therefore divide by 13. So we can adjust now, really, we can adjust for D, even 65 there, depending on the temperature settings. That T depends on the locations, and the 13 is what they have, so they would have, their average temperature would be 52, okay, 52 in their case. No, 50, yeah, 52, that's right, 52. So here is homework. Try this problem here using this chart and do some of the adjustments. It shouldn't be too difficult, right? It shouldn't be too difficult. Okay? Now, just point out, if it says 90% efficient, it means it will reduce the heat loss by 90%. So instead of 100% annual heat loss, now by doing the energy conservation measure, the revolving doors, then from 100% reduced to only 10% because it's 90% efficient. Okay, other than that, remember to account for boiler efficiency, right? Efficiency is what? Output divided by input. So that output is required to match the annual heat loss. So once you determine that annual heat, the 10% annual heat loss, you need to divide by 70% to find the natural gas use. Okay? Any questions? Ask me when we meet. All right, so to reduce, here are some of the strategies that we can reduce infiltration. Weather stripping, caulking, vertical shafts, that's for the high-rise buildings, fixed outdoor air dampers, if the dampers are functioning properly or not. Vinyl strip curtains, I don't know, have you, say, when you go to a warehouse, and when there could be forklift, right? People driving the forklift in and out of the buildings, and you will see some of the plastic and kind of transparent too, plastic curtains, and you just push through. So those can help reduce airflow in and out of the buildings. Revolving doors, rapid doors, I'm not sure what rapid doors, maybe open, close quickly, and optimize exhaust hood. Okay. Thermal heat transfer or conduction. UA delta T. I think UA delta T is an equation that we should be part of us, right? We can just say UA delta T. And rate of heat transfer equal to UA is kind of the size, the overall size, and the conductivity, right? How conductive the material is. Delta T, of course, the temperature difference is the driving force. So yeah, improve insulations. This is what we can do. Reduce thermal bridging and improve insulations, okay, to reduce the heat transfer. Radiations. The radiation is probably the most complex form of energy movement, right? Unlike the thermal heat transfer, the conduction, which require physical contact, radiation is energy traveling as waves, right? As waves. And when the radiation hits the buildings, it doesn't just go through the building directly. It's either absorbed or reflected, right? How much it is absorbed depends on the the material properties like emissivity, the total area, and the temperature as well. And that kind of leads to a chain reaction in the building's physics when, say, a roof absorbs solar radiations. Its surface temperature will really skyrocket, that go up very a lot, maybe reach even 60, 70 degrees Celsius, right? So, and that's the reason we use the light color to reduce the temperature. Anyway, so this creates a very large delta T, the temperature difference between indoor and outdoor, than the air temperature, okay? So this effective delta T and large delta T across the roof is now based on that 65 degree, for example, compared to what? 10, 20 maximum, which is really increase the heat transfer through conduction into the building. Okay, so we focus on radiation in two areas, right? The roof and the glazings. For the roof, we look at the exterior color. Is it dark color or light color? Dark color is definitely will absorb a lot of heat, so increasing the surface temperature. For windows, we look at orientations and maybe blinds, shadings, right? Curtains. If you have large window facing west without any reflective coatings or shadings, then the radiation will come into the space directly, turning the building into greenhouse basically, and forcing the cooling system to really work hard. Right? Okay. Roof. So for roof, we have to look at the balance equations. We discussed earlier, a roof is typically the largest surface area exposed to the sun, making it for the solar heat gain. Okay, so we look at the color. Okay, again, dark color absorb heat, light will reflect. So for cooling load, it's the deciding factor. Therefore, we prioritize the strategy that try to eliminate that summer heat gain. Okay, summer heat gain. So ECM, energy conservation measures for the roof, we try to use light color and increase the insulation to reduce heat, not really heat loss. Heat loss here means heat going into the building, right? Going into the building. For windows, when we on the windows, we have to remember they are only part of the envelope that energy through and two ways, right? Two ways. Thermal means low temperature conduction, convection, and low temperature thermal radiation, basically. So that's U factors, R values, okay? And to address that, what can we do? What can we do? Well, we can try to say to reduce the solar heat gain, we can use blinds and or roller shade, right? Roller shade. They would now. It's inside, usually inside. The blind, the roller shade are usually inside, so it will still trap the heat inside the glass, right? Inside the building. So really, the best would be if we can have some of the building will have the shading device outside, exterior shading device. That will stop the solar heat gain before it hits the glazing area. Okay. So this slide here will address a common indoor air dynamic that wastes energy in high ceiling space. So if you have high ceilings like warehouse or gyms, right? In many of this large volume space, we encounter what's called air stratification, meaning different layers, right? And that's due to buoyancy. Warm air will rise, cool air will go down. Okay, go down. Now, so now we got this warm air pull at the ceiling up there, right? Warm air up there, and it's kind of stay there. This is not only comfort issue only, right? This is also energy draining through the roof because of that warm air at the top. Okay, so that will increase the cost of heating, right? Because of the conduction losses and because of, if there's infiltration through the roof. This is the warm air that we like during the winter time that's leaving the buildings through the roof too. So conduction, infiltration, both. Okay. Now you can see one of the something we can do, install the fans to reduce warm air accumulating at the ceiling area. Another question to work on here, right? Another question. So 20,000 square feet industrial facility, you want to install ceiling fans, right? So to reduce the air stratification using what 0.75 horsepower. So we do need to use some energy. Okay, we do need to use some energy. Temperature is reduced instead of 90. By install the fan, we reduce to 70 degree Fahrenheit. U value is given 0.1. So now that's what R10, right? R10, not great, but exhaust 5,000 cubic feet per minute. OAT is outdoor air temperature, so use outdoor air temperature 15 degree Fahrenheit. Again, that's winter time, right? That's winter time. Heating efficiency 70%. So now calculate the energy savings. Okay, calculate the energy savings. All right. So try to do the problem again, and we can discuss if you have any questions. That's it for Module 8.